on relativity, starting with problem number 8 of the addendum. Problem 8 says, Mary is headed toward the far-off star, which is 200 light years away, at the speed of 0.992 speed of light. Her twin's name is Bob, who decides not to risk a high-speed mission like that. So this concerns the very famous twin paradox that Einstein used as a thought experiment. So one twin goes off to a far-off star and then returns. The far-off star happens to be, in this case, 200 light years away, and she's going at quite fast the speed of light, 0.992 speed of light. One twin stays here on Earth. So according to Mary, how far off is the star in light years? How many years will Mary have aged after she returns, and how many years will Bob have aged during this time? So when she returns, it's going to end up that she is much younger. She hasn't aged as much as Bob has. Okay, so let's erase these questions now that we know what they are. This is the Earth. This is the far-off star. This is 200 light years. Okay, the rocket is headed this way, 0.99 the speed of light, 0.992 the speed of light. Okay, so we could look at this from a couple different points of view. From Bob's perspective, what's going to happen is the distance to the star happens to be 200 light years, but her time in the rocket is going to be measured much slower. This is called time dilation. Here's how we can argue. According to Bob, the clocks on the rocket are what is measuring proper time. So the clock, this is the rocket's time. It's called proper time. But the clocks on Earth will be measuring relativistic time. Delta T relativistic. Okay? So this is the Earth's perspective. Okay? Okay? And then the relativistic time is greater than the proper time by a factor known as gamma. Gamma is the relativistic factor, which is 1 over square root of 1 minus beta squared. And beta is the ratio of the speed of the rocket divided by the speed of light. So beta is defined as V over C. Okay? So the thought experiment that Einstein used for this is that if there is a clock on the rocket, which is made up of two mirrors, a light clock, and imagine the light goes up and down in this clock. So imagine a person in the rocket that is going at a certain speed decides to measure time with what's known as a light clock. So all you have is basically two mirrors, and then he reflects the light up and down, up and down, up and down, up and down, and depending on how long it takes the light to go up and down, that's how he measures time. Okay? So that's how he's going to be measuring time. Now, according to the person in the rocket, in his reference frame, the light is going to be going up and then down. It's basically going to be making a vertical path. However, someone on Earth in a rest frame is going to be seeing what? Okay, from the perspective of the Earth's reference frame, the rocket's time is going to be doing this. By the time that the light beam starts to travel up, the mirrors are a little bit ahead of where they were when the light beam first started. So he's going to be seeing this kind of a path. The light beam leaves, okay, by the time it reaches the upper mirror, the light beam is over here, and then by the time it comes and bounces back, the light beam is over here. So Einstein said that the speed of light never changes with respect to any reference frame. So the speed of light is still the same here as in this reference frame, but the distance that is traveling is farther, right? So since it's traveling farther distance, its speed is the same. According to a person on Earth, it takes the light beam longer amount of time, which is known as relativistic time. We call the person in the rocket's time proper time, okay? And the person on Earth, we call their time relativistic time. Why? Because the person on Earth is seeing a relativistic effect. He's seeing the light beam travel a farther distance, take a longer time, okay? The reason we call the rocket's time proper is because, according to him, he is not moving. The event is occurring in the same spot. The light beam is going up, it's bouncing back, it's occurring in the same spot, so that is known as proper time, okay? So his time is shorter. By how much shorter? Well, now we're going to calculate that. The relativistic factor here is what? Let's calculate that. Gamma is going to equal 1 over divided by 1 minus, what is beta in this case? Beta is the ratio of your speed to the speed of light, so it's 0.992. 0.992 squared. So now we got to do 7.92155. So the relativistic factor is 7.92155. So whatever time the proper is, the relativistic time will be larger, okay? So according to a person, to Bob's perspective, how long should it take the rocket to go and come back, okay? Well, according to his perspective, the star is 200 light years away. The speed of the rocket is 0.992 c, and he's going twice. So you basically just divide it, okay? So the delta t relativistic is equal to what? Okay, so delta t relativistic will equal, it's going to be 200, 2 times 200 light years, right? Because it's twice the distance. And then you divide that by the speed of the rocket, 0.992 c. Okay? Now some people, when they're doing these kinds of problems, they think that they have to change light years to units of meters. And then they have to change speed of light to units of meters. Okay? But you have to remember that a light year is defined as what? A light year is already defined as the distance that it takes for light to travel 1 year, right? So it has in it already built in c. So this actually cancels this, and it gives you in units of years. Okay? So if you want to do it officially, you can say this way. 1 light year is the distance that you travel for 1 year traveling at the speed of light. So it's the product of c and 1 year. And then light year cancels light year, c cancels c, and then that's it. You don't need to put down what is a light year in terms of meters, what is the speed of light. C and C cancels, and then you end up getting years. Okay? So you have 2 times 200 divided by 0.992. So it's going to be 403.226 years. Bob, when he does his calculations, he says, my twin, by the time my twin goes and comes back, I will have aged 403.226 years, therefore I will be dead. So he probably says his last goodbyes and he says, I'm not going to see you. But you will still be living because you will be measuring proper time. By what factor? By a factor of 7.92155, right? So what is the proper time equal to in this case? Delta t proper is equal to delta t relativistic divided by gamma. Okay, so now delta t proper is going to be 403.226 years divided by 7.92155. This is years. This is a unitless constant. It has no units. So when you divide them, you still get years. So we take the answer that we got divided by 7.92155, and we get delta t proper 50.9 years. Okay, so that means if Mary was 20 years to begin with, she'll be 7 years old when she comes back, she will be living. And of course, everyone here on earth will have died and she will come back to a new world, okay? Now, how can we analyze this from Mary's perspective? Okay? Mary's perspective, from Mary's perspective, she is the one that is standing still. Okay. Of course, what happens is when she first takes off, she knows she's the one that is accelerating, right? And then during the portion when she's going at constant speed, the distance between Earth and the star have been shortened, and they're passing by. So she thinks this distance here is shorter. Okay, that's called relativistic contraction. Okay, shorter. So therefore, the distance is something like much shorter. So let's say the whole thing has been contracted by a certain factor, and then we're going to find what that factor is, right? And the whole thing is going this way. So if she was originally headed that way, she accelerates. During the acceleration, she knows that she's the one moving. Other than that, when she's coasting, she sees this whole distance as shrunk and moving this way. Then what happens? When she goes to the star, she has to decelerate, right? She's got to decelerate. During that portion, she knows that she's the one that is slowing down. She stops, she turns around, she heads back the other way, so she accelerates. Okay, and then during the coasting stage coming back, this whole thing is moving the other way. Okay, going back this way, and then this time she's pointing this direction, and the whole thing is going the other way. Okay, so here's what happens. According to her, it is her that is, during her coasting stage, it is her that is measuring relativistic time, and the Earth should not age as much. However, because there are turning points that occur, at the turning points, she realizes that she's the one moving, okay? And there's what is known as simultaneity of time. Basically realizes, remember when in the questions I was going over this, I said when something is moving this way, if there are two clocks, if there's a clock on Earth and there's a clock on the star, which clock will be ahead? Well, if you put a light beam over here, if the system is moving this way, right, as she is headed towards the star, the system is coming this way, right? So if you put a light clock in the middle and the light beam goes in two directions, right, the clocks on the star start first, the clocks on Earth start later. Okay, so that means the two times are not simultaneous. So what basically happens is she accelerates, the whole system comes to her, right? And then she stops where the star is. The time on the star is now way ahead of the time on the Earth. She turns around and the whole system comes toward her, right? So when she turns around and she heads the other way, now the Earth is coming this way, the star is headed that way, right? And now the clocks on Earth seem like they are ahead of the star. So there are several bumps that occur here, several bumps of the times, right? So the eventual effect of all of this is by the time that she arrives here, okay, she ends up and she comes outside, she is younger than people on Earth, right? But the reason for being younger than people on Earth are disagreed between them. Mary says the reason that you have lived longer is because, first of all, the distance has been shortened. Therefore, the path that I took was not as long as you guys think I took, right? The distance that I traveled was much shorter than you guys say. And the other reason you guys lived longer is because the reference frames, the star and the Earth, you guys could not agree on the time. There were differences of the time, and therefore the Earth bumped forward in time because of issues with simultaneity. And therefore they will both agree on the fact that the Earth people have aged longer. Okay? So let's do a quick calculation here. According to her, how long should it take her to go and come back? Well, according to her, this distance has been shortened, right? So the formula we use is length relativistic is equal to 1 over gamma length proper. Right? What is the length proper? The length proper is the original length that they had. The original length when they're at rest, the 200 light years. That was the length proper, right? But according to her, she sees that length as moving towards her in either direction, right? That length is going to be contracted. So we call that relativistic contraction. So L relativistic. We're going to use the same gamma factor that we used before, okay? So that one was what? 1 over 7.92155. And then the proper length is 200 light years. 25.248 light years. From her perspective, how long should it take her? Since she will call that relativistic time, the time that she's experiencing, so this will all come this way and then go back. Her time will be relativistic time, so delta t relativistic is equal to what? Twice the distance, 2 times 2, 25.248, divided by the speed with which the planet and the star are moving, which is 0.992 c, 0.992 c. And of course, c and light year will cancel, and then we'll get the answer in years. So I'm going to take the answer that I got, I'm going to double it, divide it by 0.992. Delta t relativistic is equal to 50.9 years. According to her, she should live 50.9 years. People on Earth should have lived less. However, because of issues with simultaneity, the Earth people lived longer because they could not agree with the reference frame of the star and the Earth, and they were not simultaneous with each other. Okay, so now you realize how to approach these kinds of problems, and you can prod more and learn more about this, research about it. It's very, very confusing at first. It's kind of unbelievable that this could actually happen, but it really will happen. If someday we are able to go near the speed of light, this thought experiment will actually work. Okay, so it's really weird that you could actually go into the future that way. You come back, everyone on Earth is dead, but you are still alive. Okay, thank you very much.